Hello everyone, welcome once again. Today I'm going to show you how to make a 8-bit adder. In my previous class, if you all remember, I have shown you how to make a half adder. Then this is a half adder, and we have added this clear logic to make our circuit quick. Okay, why we need a clear? Because we need to control the complete circuit, and anytime if we have to bring or at a reset state or a zero state, we have to use this clear button. Okay, so if we give a clear zero, with the help of this AND gate, the zero will pass to this XOR and this AND, and whatever the input will come here, that is not going to move forward because here you have again one zero. Okay, so because of this zero, okay, you will be getting always output zero, right? So you are not going to get any other output if input is zero, of clear input is zero. So I can say that my circuit is with clear input active low. So it is working on zero input. Okay. Similarly, we have converted this half adder and we have mm, make it of this half adder. We have designed a one bit full adder. You can see here. This is our one bit full adder. Okay. So this is the same. If you push if you push it into the symbol, you will get the same circuit. Okay. So using this two half adder, we have made a full adder. Okay. And again, that every input we have given AND gate. Why? Because I want my each and every signal should be controlled. Okay. That is controlled by the user. That is control should have at the end of the user. Okay. Similarly, at the out end side, you can see here. Okay. Again, whatever the input coming at some zero, it is not going to pass unless until if we are giving one here at the input of AND gate. So if the input of AND gate is zero, again the output is zero. Okay. So in this way, we have designed the clear circuit for full adder also. Now we are going to design a circuit of 8-bit adder. Now, what is 8-bit adder exactly? Okay, so let me first share you something about 8-bit adder. So what is bit basically? So there is one input like this. This is A input. And if it is carry zero and a single digit, then it is called a bit, single bit. Okay, single bit. Correct? Single bit. But if we have any input A is line and if we have a multiple value, then it is called a multiple bit. Okay, so this is called 4-bit and this is called 4-bit. So here what we are going to do, we are going to make a 8-bit adder and we are giving input A and input B. Okay, input A 1 0 0 1 0 0 0 1. So 4, 5, 6, 7, 8, and anything 1 1 0 1 1 0 1 0. So 4 and 4 8. So this is called basically 8-bit. Okay, so and the sum and C out. So sum will be your again 8-bit and output is your C out is basically your 9-bit. Okay, right? So our task is to make a 8-bit adder. Okay, not a 4-bit, 2-bit, 3-bit, because in our sign calculator, we need basically we need a 8-bit component. Okay, either it can be a adder, subtractor, multiplier, divider. Okay, so let's start, and I hope it is clear to you. Now I'll go back to my Xilinx ISE. Again, this is the product designed by Xilinx. They have basically developed this tool to configure their FPGA device, which is mounted on a green card. Okay, so we need to program it with the help of this tool. Okay, so why this tool is best for the student? Because the student can easily learn all the digital circuit, and if they have designed something, they will never forget. Okay, so for 4-bit adder, for 8-bit adder, again, go to the design window, go to the hierarchy, right click, new source, schematic, type here bit A, with 8 adder with clear input. Okay. So click on next, finish. Okay. Make sure that you have created the symbol of each and every component. If symbol is not created, okay, then you can do it again. For example, if symbol is created, uh, your tool will give a warning or message that symbol has been created. It cannot be overwrite. Okay, so let's do one thing. First, create a symbol of half adder. Right click, run. If symbol is created, it will give a warning. Okay, symbol not created, so it has been created. And now, same thing. Let's try for the half adder. If symbol is created, it will give a error. Okay, you can see here before creating the symbol, it's showing that green color. That means symbol is created. But let's do one thing once again. So it's showing the red. That means you cannot again create the symbol if symbol is already created. Now go to the 8-bit adder workspace. Now you can see that workspace is completely blank with no dotted lines. Now you can see that dotted lines is mentioned here. Okay, so this is called workspace. You can increase the size. How you can increase? Double click. So this is the sheet size. So I want my size to be increased in length. So I will select 34 cross 22. And you can see that a little bit increase in the length. Okay. Now I will again go to the zoom in and I will click some 3 to 4 times to get this dotted window. Okay. Now I will call 8-bit adder. Sorry. Now I will call a 1-bit full adder 8 times. Okay. Please remember I'm making a 8-bit adder. Okay. So half adder clear is created, not full adder. So let me again check this. Right click, set as top and create a schematic symbol. Now symbol of full adder is also created. Okay, so I will go to the symbol. I will select this and I will see that, and I will see that there are two symbols are present here. One is full adder, one is half adder. So click on full adder and you can, okay, okay, so like this. Okay, so again, go to the symbol and please add 8 times your full adder. 8 times means 8-bit. So 5, 6, 7. 1, 2, 3. So how to remove the shadow? I press escape. 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So I need one more to make it. No, no. 0, 1, 2, 3, 0 to 7, 3, 4, 5, 6. So I need one more. Okay. So go to the symbol once again and select full adder. Okay. Now, first I will add I will add the clear logic. Okay. So I will start adding the AND gate. Select all symbols, bring AND to here. This, okay, you can like this. Oh, one mistake. This is like this. Okay. Okay. So basically, I have to add a AND gate to every input so that I can pass the clear logic, okay, like this, like this. Okay, and same and logic I have to add at the output side also. Okay, like this. Okay. If you will not add a clear logic, again I am mentioning again and again, you will lose the control on your design. Okay, because initially it will help you to identify that all signals are intact, are connected properly or not. Okay, because see, I'm telling you very openly. Basically, earlier you have two, three lines, then you have eight, 10 lines. Now with this circuit, you will have at least 50 to 60 lines. Okay. So you cannot see that by mistake if any line is not connected, then how you will come to know. Okay. So if by mistake if any line is not connected, if you will give a clear zero, if that line is not connected to the clear, that will be remain unchanged. So in that way you can identify. That is why the importance of clear is here. Okay. So I will show you later on. So I have connected the AND to every input and to every output, right? So this is now let's start connecting one input of AND gate. Every input of like every one input of AND gate with clear. So choose wire here, okay, and then connect this. Okay, you cannot see dotted line, so you can do zoom in to see the all dotted. Okay, again go to wire, and select this, select this, select this, select this, select this, next, this. Okay, so now let's connect all uh, all clear input to one line. Okay, okay, let's connect all clear input. Okay, escape. See, I am connecting all clear input to one point. Okay, like this. Why? Because I want zero to be passed from AND gate to every block. Okay, so this zero will pass to full adder, and from there full adder to half adder. Okay, then again this also you have to connect one input of every AND gate to the clear input. Okay, like this, like this, like this. Like this. Okay, got it. Okay, Oh, so now I have to connect the B. This is the A, this is A, this is B. Okay, A0, B0. So this A0 is connected, but B0 is not connected to the B in. So we have to connect this B0 with the B in. Okay, like this. Okay, you have to be very like very careful while connecting, because maybe you can connect the output to any other input. So in that case, your logic will be different. Okay, you cannot get the correct output. Okay, so here I have connected the B, that is the second AND gate with the B input of every full adder, one bit full adder. Okay, now I have to give basically I have to give IO marker. So this is my IO marker. So just select IO marker and keep it put at the input and click left click. Okay, okay, okay. This is not taking the input marker. So I will little bit I will extend it. Okay, okay. No, okay. Let's okay. No, IO markers can only be connected to the branch endpoint. Okay, it's showing to the branch endpoint. You can zoom in and then you can again. No, no, some issue. So let's try once again. Oh, this time I got it. No, because maybe this square box is basically colliding with this line. Okay, that is why your IO marker is not connected. Okay, okay, like this. No, press escape and okay. A0, B0, A1, A2, B1, B2. So press escape to get the shadow of the input marker. Now left click, double left click, click on nets and give A0, right? A0. Then again B0. Okay, A1, A1, B1. Okay, A1, A0, B0, A1, B1, B1. This is my A2. Okay, so I'm going to change the name of every input and IO marker with respect to the input and output. That is a 7-bit 0 to 7A and 0 to 7B. Okay. A2, B2, A4, A5. No, no, A4, B4, A5, B5, A6, B6, A7. and B7. Okay. So similarly, I have to connect the IO marker on the output side also. So let's connect IO marker at the output side. Yes. Okay. Okay. So now it's time to give a name. So right click, rename port. Okay. S0, Control A, Control C, copy, Control V, S1, Control V, S2. We are very close to the completion of design. S3. Okay. Oh, no. S3. Okay. Apply. S4. S5. S6. S7. S8. Sorry. We need to check. Sorry, this is C out. This is C out. Last one is basically C out. Okay. C out. So now, not count, this is C out. Okay. So minimize this. Now, only one thing is left that I have to connect. Now, actually, I have not given basically two things here. I have not connected the C out to C in, which is pending. And then I have to connect all the clear to one port. Okay. So bring it here, bring it here. Okay. And double click, clear. Okay. So now you can see here if I, oh, value is not changed. Clear. Okay. So if you select this line, you can still one point is unconnected. So I'm going to connect it again. This basically the clear in of every full ladder is not connected. Okay. Either you can connect on upper line or you can connect on below line. Okay. You have to be do it very carefully. Otherwise, any wrong connections can give you a good trouble. Okay. Okay. So all my C out, all my clear is connected now properly. Okay. Now it's time to connect C in of my first flip flop because as we know that full adder and half adder both are two input device. Full adder is not a three input device. Virtually it's look like a three input, but actually it is a two input. The third input of my first full adder is not getting any output from any past. Okay, so we will give we'll make this either zero or we will connect with the ground. Okay, so I will search for ground, G and D. Okay, so Control R. Okay, so this is not connected. Now I will see. I will try once more. Ground. Connect. No, no. So in that case, if ground is in that case, if such connections give problem, then do one thing and try to connect the symbol outside from the from the from if it is if any symbol is basically why I'm getting error because that symbol is basically touching this wire. Okay, so that is the reason I'm not able to connect it. So I will do it once again like this. Okay, now this time my ground is connected. Okay, now C out to C in. As I mentioned that whatever the C out will come, that C out will go to the next full letter C in. Okay, okay. If let's see if this. Okay, this is auto router. If auto router will able to manage connect will able to connect it, then it's okay. Otherwise, you have to personally help the design. Okay, you have to personally look each and everything why your connection is not working properly. Okay, yeah. This C out, C in, this C out, C in. This C out will connect to the C in. You don't have to worry about the connection. The tool will automatically take care of it. Okay, this C out to C in, and this is last C out to C in. Okay. So finally, my full header is completed. Now I can say here I am getting max more than 50 signals. Okay, this is looking very meshy, but there is no other solution. Okay, so again to verify that your clear is connected to all the clear input, then you can just click on the wire and you can see that this red wire is connected to every clear input of the block and also the every one input of the AND gate. Okay, in this way you can verify. Okay, now let's go for the simulation. Okay, now you can see here that your tree is created. Okay, so 8-bit adder is made up of one full adder and full adder is made up of two half adder. In this way, your tree is created. Now go for the simulation. Select simulation, select 8-bit adder, right click, run mode. Okay. So in simulation, you will find first one thing is that your resolution window is up to the uh, 1 lakh picosecond. Okay, I'm sorry, up to the 10 lakh picosecond. So you have to reduce it. Okay, you have to reduce it for up to the 1 microsecond. So how you will do it? You have to click one time on zoom to cursor, then one time on zoom to full view, and then three time on zoom out. One, two, three. So 1 microsecond resolution you have received. Okay. Now you can see here all my outputs and all my output signals or intermediate signals are red except this one 75 because this 75 is actually is this signal name is basically connected to my ground. So ground value is 0. So you can see here the by default the 0 is here. Okay. Now we will start forcing the value, but before that we will check that my clear is connected to every output and internal signal or not. So I will give 0 and this is the force window run for the time specified on the toolbar. And you can see that your all intermediate signal and output signals are 0. That means you are getting, that means this clear is connected to every single block or every single components. Okay, now I will start giving the value. So A0 here, A0 is MSB. Okay, A0 is LSB. Basically, your A0 is A7, A6, A5, A4, A3, A2, A1, and A0. And B7, B6, B5, B4, B3, B2, B1, and B0. So A is LSP, A side is MSP, and A7 is MSP. So basically, you read from here, okay, MSP and LSP. Okay, so I will give 0, 0, 0, 0, 0, 0, 0, 1, and again 0, 0, 0, 0, 0, 0, 1, 0. Okay, so basically the output will come 1, 1, 0, 0, 0, 0. Okay, so I will give 1 and 2. Okay, to verify the 8-bit half adder. So either you start from A0 or from A7. Okay, how to force the value? Click on force constant, then type here A0, then type here 1. Okay, apply, then remove 0 and add 1 and mark it 0. Click again apply A2 0 because I want same value 0 again. So again click apply A3. I want again 0. So click apply A4 again 0. Click apply A5 again 0. Click apply A6 again 0. Click apply and A7 again 0 and click apply. Okay, click OK. And B0, I will give a 1 0. That means 2. So the first B0 is 0. Apply. And B1 is 1. 1. Apply. And then from B2 onwards, output is 0. B2 onwards, output is 0. 0. Apply. B3, 0. B4, 0. B5, 0. B6, 0. And B7, 0. So I have given 0, 0, 0, 0, 0, 0, 0, 1 and 0, 0, 0, 0, 0, 0, 1, 0. That is 1 and 2. Okay. So this clear is still 0. So click on this run for the time specified on the toolbar. I will see that you will see here that all my input is now credited with the given value. So you can see here B0 is 0 and B1 is 1. Now I will erase the value of 0 from clear and I will give it to 1. So force constant and give it to 1. And in my output, we will see that S0 and S1 is 1, 1. See here, S0 and S1 is 1, 1. That means my design is correct. So in this way, I have shown you the simulation. I have shown you how to design the circuit of 8-bit adder. Basically, this 8-bit adder is very complex because uh, as I'm giving you demo, so I want to give you the clear picture that how to connect the each and every block. And there is another way also, that is a way known as that multiple bit on single line. So in that case, I can reduce number of lines. Okay, I can reduce number of lines. So that will be look very simple, and even that forcing the value is also very easy. But here, when I am creating in the input for every single line, then I'm getting too many wires, and also the forcing the value will take time. It's taking time. Okay. Now if you keep your cursor here, you will find that the name of the first block is instance excellent1. This is type full adder, and the input A in, B in, C in is connected with the wire 229 and 75. Okay, and input clear in is along with the output sum and C out, means the wire of the intermediate signal of C out and C and sum is connected with the excellent 76 and 10. If any of the line is not working, okay, you can easily debug from here. Okay, so please make the circuit. If you're facing any problem, please let me know. I'm there to help you out. Okay, so this is all from my side. Uh, we are working very hard for you guys. Okay, these things are easily available, but no one guided you. But now I am trying to guide you how to basically make your digital strong. Okay, so this is just the basic. This is just we have started with the adder. Similarly, we are going to make a subtractor. mux, demux, decoder, encoder, 2s complement, and then we will add it and make our first project that is called a sign calculator of a plus b and a minus b. Similarly, we will design the sequential circuit, counter, shift registers, and everything. Right. So this is all from my side. Please stay tuned, be in touch, be focused. Please prepare your schedule and keep working on your schedule. If you focus and if you do it everything properly in given time, definitely you will achieve the success. Okay. So this is all from my side. Very soon I will show you the another demo that how to design the multiple bits. And thank you very much. Bye everyone.